at using Lagrange multipliers. And what I've done here is put some more examples of the more difficult type at the end. And this is an example of a pretty standard one. I want to know the absolute maximum and minimum value of this polynomial, subject to the constraint that x squared plus y squared is less than or equal to 16. So if you can imagine on the floor, on the xy plane, there's a circular disk of radius 4 centered the origin. And that column, including the points inside it, go vertically upwards and they meet the surface, the 2x squared guy. Now, somewhere in that region, there's at least one point that has a higher z value, right? It's higher up than anybody else. That's the absolute max. And there's going to be one typically lower than anyone else. And let's get started. So we find the critical points by solving when is the gradient of f equal to lambda take the gradient of g. So this is the partial derivative of x and y. And this is lambda times the g of x. Technically, you don't need to worry right now about the 16. Think of that as being your g of x. So it's going to be the partial derivative of those two. And so I now have, if you differentiate this function with respect to x, you get a 4x, you get a nothing, and you get take away 4. And if you then do it with respect to y, you get a 6y. Yeah. And that's going to be the lambda. And if you differentiate this with x and then this with y, you've got that. Are you comfortable about what we've done so far? Right. Now, to solve this, essentially, it's going to be a system of equations. You take the x's, right? The x component of the vectors, I should say, and you write down the relationship, which is that one. And then you take the y guys. Too late now. I should have called that 2 lambda y, but it's no biggie. So far, so good. So this is essentially the system of equations that we're going to work with. And we do two situations. The first one is you choose or assume that lambda could be 0. Now, if lambda could be 0, which it could happen here, this equation becomes 4x take away 4 equals 0. And this one here becomes essentially 0 equals 0, which really doesn't tell me anything. But this one here tells me that x could be 1. Okay. So I'll go to my constraint function, which is that one. And I'm looking for what y values would work. And I'm going to put in 1 here plus y squared. And I'm going to talk about the boundary. And so that gets me this one. So I have a plus 15 and I have a negative 15. So I'm going to get a 1 comma square root of 15 and a negative 1 comma, sorry, a 1 again, and a negative square root of 15. So here are two critical numbers. So we might get the absolute max and the absolute min at this point. So here's an example of lambda equals 0 actually generating a result, something that could work. We then assume that lambda is not 0, which is the typical place where you get all your stuff. And I'm looking at these two equations and it's getting a little bit messy. So I'm going to take equation 1 and divide it by equation 2. And I get 4x take, I get 4x take away 4 over 6y is going to be 2 lambda x over 2 lambda y. These cancel. and I can cross multiply. So I get 4x take away 4 times y equals 6xy. And I get 4xy take away 4y equals 6xy. I get this fella. And I'm looking, I'll try to find some help here. I'm looking at what the heck's going on here, and I realized I should have done something different. I should bring everybody over to this side, in which case I get 2xy plus 4y is 0. And that pulls out, there, I got some. Are we good with what I've got so far? Now, what does this tell me? Well, it tells me that y could be 0. And this one tells me that 2x plus 4 could be 0, which is another way of saying x is -2. Now, when y is 0, I go to the constraint function, and I find out that x squared has to be less than or equal to 16. We're only interested in the equals part. And so I get x's plus or minus 4. So that gets me 0, 4, and 0, -4. And if I make x equals -2 and I plug it in here, I get 4 plus y squared. Again, you're only interested in the boundary. That gets me y squared equals 12. So y is plus or minus the square root of 12. And so I get -2 square root of 12 and -2 minus square root of 12. So those are critical points and those are critical points. So we have actually got 1, 2, 3, 6 altogether. So you then set up a table and you find the original function at each of these 6 points. And whatever answer is the biggest is your absolute max, and whatever answer is your smallest is the absolute min. And I'm seeing what they've got as an answer here, so I don't have to do this. According to them, the absolute maximum value that you're going to get is 45, and the absolute minimum value you're going to get is -9. And did they tell me where they happen? This one happens at the -2 plus or minus square root of 12. So both of them get you that. And this one happens at this makes sense.
Shouldn't that be 4, 0 and -4, 0?
Which one? Here?
Yeah.
Yes.
X is plus or minus.
So evidently, one of my calculations is a bit out, but that's fine. You get the smallest. That doesn't even match their answer. Oh. The question I have is not the question they've got, because they've now changed the numbers since the first time I've wrote it down. So you will have to calculate those guys, and one of those guys that we wrote down is going to be your absolute max, and one of those guys is going to be your absolute min. I can't tell you which one it is now because it's gone and changed the question. Go for it. Well, 8's a video, I don't want to do that. 9's a video, you can watch that. Let's do some puzzle ones and then I'll finish with another one of those. Right at the beginning, I got a couple of puzzle ones. So this is question 1. Use our technique to find two positive numbers whose product is 196. So you have just given me the constraint. And the function that we're going to be, in this case, minimizing is the sum. So the question says, use Lagrangge multipliers to find two positive numbers whose product is 196 and whose sum is a minimum. And enter your answer or answers as a common separated list. Okay. So the gradient of f is lambda times the gradient of g. This guy is going to be 1, 1, and this guy is going to be y, x. So 1 is equal to lambda y and 1 is equal to lambda x. If you divide these two guys, 1 is equal to y over x, which means that y will have to equal x. And since x times y, according to the constraint function, has to be 196, then x times x has to be 196. So x squared is 196. And that makes x square root of 146, makes x equals 14. So, why? Because they told me it's positive, because I could have got negative 14. Right, I know x is that fella. I can use this to figure out who y is, and it's not a surprise that you get 14. So the combination that works is make both of them 14. And your answer will look not like that, but like that. Comma separated lists, right? So you don't put a little bracket around it, although it makes sense that you should. WebAssign just doesn't want the brackets. So we've just found two numbers, positive numbers, that multiply together give you 196, and their greatest sum is happens when these two are both 14. They don't even want to know what that greatest sum is, but if they did want to know what it is, wouldn't the answer just be 28? Okay, let's try the next one. Puzzle 2. Use Lagrangge multipliers to find the dimensions of a rectangle with perimeter 160. So if you make this x and you make this y, the constraint function is 2x plus 2y equals 160. And we want to make it the largest area. So the function for the area is xy. So we're trying to maximize this guy subject to that constraint. Do you see how I took the written information and created the constraint function? The perimeter has to be 160. And the function we're trying to maximize is xy. So Lagrangge multipliers, give me that. And if you differentiate this fella, you get y, and differentiating the other way, you get x. And this fella, you get lambda, and you get a 2 and another 2. So y equals 2 lambda, x equals 2 lambda. If you take 1 divided by the other, and I'm kind of getting deja vu here, but isn't it kind of obvious we're going to get a square anyway? Great. So I know that y equals x. All I need to do is take the constraint function, replace the y with x, So x is going to be 40 and y is going to be the same. So if you want this to be true, don't you make a square 40 by 40? And that will get you the maximum area. We're done. Aren't those identical questions to Calc 1? Can you remember doing ones just like that? Slightly different approach, but same result. Right, question 3. We want to find the point on the line y equals 2x plus 8 that is closest to the origin. Interesting. Try and draw what's going on. Here is the line 2x plus 8. Here is the origin. We're trying to find the point on the line, I'll call it P, that's closest to this straight line. Right, so can you imagine it won't be this one, isn't that much longer, and it won't be this one, isn't that going to be much longer? But can you imagine that as you travel along this line, aren't you going to hit a sweet point there? Great. Now, the distance from O to P is the square root of, well, since that's the origin, and I'll call that xy, it's basically just x squared plus y squared. And we typically call this guy d, d for distance. And we typically square it. So that is going to be the function that we need to minimize. And the constraint function is that y has to equal 2x plus 8. So basically, right, this fella here is going to be our g of x. Now, we have to kind of rearrange it a little bit. So it's going to be 2x take away y plus 8 equals 0. And this piece here, because the number doesn't matter, is going to be our g of x. So, are you happy about how we found the optimization function, which is basically the distance from the origin to a random point on the line squared, d squared? And that the constraint function has to be written in such a way that we have a function of x and y. And I just rearranged it this way to get that particular shape. So we are looking at this function. Subject to this constraint. I guess I could rearrange it that way. So the gradient of f is going to be lambda times the gradient of g. Partial derivative with x and y. Lambda. Partial derivative of g with x and y. This fella gets you 2x comma 2y. And this fella gets you 2 and negative 1. Differentiate with x, you get 2. Differentiate with y, you get negative 1. So we have 2x is 2 lambda. 2y is negative lambda. Now I've done a really bad? No, but I got away with it. Shouldn't we be doing lambda equals 0 and testing if that one worked? I should have done it for the other two questions. Can you trust me if I had done it for those other two, we get the silly answer that x and y are both 0 and that doesn't work, right? Now, in this case here, if I made lambda 0, wouldn't I get x is 0 and y is 0? And wouldn't that not fit this one, the constraint? So it doesn't work. So I can take equation 1 and divide it by equation 2. Do a bit of cancelling here. And you get x over y is essentially what, -2. And that makes x equal to -2y. And I'm going to use that relationship along with the constraint function to solve. So I know that 2x take away y has to equal -8. But if x can be replaced by -2y, then we get this, which in turn gives me this, which in turn gets me that guy. And the x coordinate is -2 times that guy. So there is my critical point. Oops. Here we go. There is my critical point. And in this question, that's all they wanted to know. So this guy up here, he has an x coordinate of -16/5 and a y coordinate of 8/5. And that kind of looks about right when you see the thing. Are we good with that question? And try and remember to always do the lambda equals 0 test, even if I forget to, because there's going to be a question where I shouldn't have forgotten. I should have done it, because that's actually the one that does the solution. It's always when you forget to do it that happens. How are we doing so far? I know I've been a little bit on the quick side, but we kind of want to try and catch up back to schedule. Are we good so far?
Can I see that piece of paper real quick? My part's been blinking.
Sure. Must I find it?
I think you got rid of it just now.
But I put it on top of a whole pile, so once you do that, anything can happen. Here we go. There it is. Well, that's one of its pages, and the other one's probably underneath. No. There we go. There we are.
Okay, I'm good.
Okay. So I'm going to do another one of those horrible polynomial ones, because they just take forever, but you know, gotta do them. See if I've not done that one. Done this one. No, I haven't done this one. Done that one. This one. Okay. So we're being asked to find the absolute maximum or minimum of this polynomial function. and it's subject to the constraint that x squared plus y squared has to be less than or equal to 49. So this is my g of x. Obviously, this is my f of x. So far, so good. That's just a setup. The gradient of f equals lambda, the gradient of g. If you differentiate with respect to x, you get 2x nothing, and you get a plus 8. If you do it with respect to y, you get a 2y minus 8. And we have a lambda times a 2x and a 2y. And so my two equations become this guy is 2 lambda x, and this guy is 2 lambda y. So far, so good. If you make lambda 0, you get a possible solution, a possible critical number. You get x is -4, and you get y is +4. So a possible critical number would be that guy. Now going to test it against x squared plus y squared needs to be less than or equal to 49. So I'm looking at -4 squared plus 4 squared will have to be less than or equal to 49, and 16 plus 16. And the answer is yes, that one works. So this is a critical number. It's the only critical number that is going to be inside that value. All the other critical numbers are going to be in the boundary of the circle. So we'll be looking at equals 49 from this point onwards. Oh, if you're wondering what you're finding when you make lambda equals 0, you're finding the absolute max and min of a function, or at least I should say the local max and min of a function with that restriction. So if you took that away, that would be the only possible critical number, right? That's the only place where the first derivative with x and the first derivative with y are both 0. So we move on to our second phase, where we use these two equations. I just write them down again, I think. And we are assuming now that lambda is not 0, because we tried it out with 0 and we got an answer. Now we can say, well, what happens if my lambdas look like x's, don't they? Lambda's not 0. So I'm going to take equation 1 and divide it by equation 2. So we have a 2x plus 8 over a 2y minus 8. And it's 2 lambda x over 2 lambda y. And there's actually a lot more cancelling than you would think. They cancel and they cancel, and you get x over y. I'm just going to leave these two guys alone, even although I could divide top and bottom by 2. So I do a cross multiply. Distribute the y's. We get that. So far, so good. Okay, what do you think I'm going to do to both sides next? What could I do to both sides next that's going to make our life easier?
We could subtract 2xy from both sides.
And couldn't we now divide both sides by 8? Do you see that what we found is that if you're going to get a solution, doesn't the y have to equal negative the x? You see, we've got a relationship between the two. So I'm going to put y equals negative x into the constraint function, but we only need to look at the boundary, right? The equals 49. The inside part has been solved by the lambda 0. So now we only need to look at that. Now, if I tell you that y is negative x, then you can replace it by negative x. And what that gives us is a way to find the solution, at least in terms of x. If you divide both sides by 2, and then you take the square root, you get a plus or a minus, right? And the square root of 49 halves, which could become that guy, agreed? So I have some candidates. One of them is that the x is negative 7 over root 2. And the other one is x is positive root 7 over 2. And since the y coordinate is the negative of the x, for this one, the y coordinate becomes that guy. And for this situation, the y coordinate becomes that guy. And so I now have this ugly guy. And this ugly guy. And I also have this guy. So it looks like there are 3 critical points. One of them is negative 4, 4. The other 2 are negative 7 over root 2, positive 7 over root 2. And the last one is positive 7 over root 2, comma, negative 7 over root 2. And I'm going to cheat here. If you use this one, the answer that you get is 49 plus 56 root 2, which is about 128.2. If you do this one, you get 49 take away 56 root 2, which is approximately negative 30.2. And if you use the 4, 4 guy, you get negative 32. So the absolute max is this guy, and the absolute min was this guy. Is that right? No, negative 32 is the absolute min. That's fair, right? That's smaller than that, right? And so what does it look like? In Weber sign, you've got maximum, and you've got your absolute minimum. In the absolute minimum, you just put in that number, and the absolute maximum, you put in this guy. And the only reason that these were turned into decimals was it wasn't that clear, especially this one, whether it was smaller or bigger than negative 32. So you kind of had to need to, put a value on it to decide. You are allowed to ask questions. So do we have any questions? Okay. Almost finished this section. I think to finish with, will I do another one? No, that's pretty standard. Video, no, you can watch the video. Video, not watch that. Oh, it looks like I've only one question I need to do then. So there's a version of question 4. And you got a thing that looks like this. And this distance is the length of the package. The girth is the circumference, right? And the package to be mailed uses certain postal service. And it may not measure more than 90 inches in length plus girth. So length plus girth. And it's not allowed to be more than 90. So that's another way of saying it must be less than or equal to 90. Well, I'm not going to use length and girth because I'm going to call it x plus y. And I will remember that length is x, and this circular distance, the girth, is y. I can handle that. And use Lagrandge multipliers to find the exact dimension in inches of a cylindrical mailing tube, and we have to find the greatest volume. Okay, so if you're doing the volume, it's essentially a cylinder, right? So the cylinder is pi times radius squared times, essentially in this case, length. Well, that's pi, and that's x. But the radius is a little bit of a problem, because I'm going to find the girth of this thing. So the girth, which I am calling y, is 2 pi r. That means that radius is y over 2 pi. So this is y over 2 pi. So I get pi y squared over 4 pi squared x. And that becomes xy squared over 4 pi. There is my f of xy guy. So if you make the girth y and you make the length x, then the formula is in terms of this guy. And your constraint function is basically this guy here. So the gradient of f is going to be lambda times the gradient of g. Partial derivative with x and y, and lambda times the partial derivative of g with respect to x and y. Now this here is my f of xy guy. If you differentiate this mess with respect to x, you get that guy. And if you differentiate it with respect to y, you essentially get that guy. I know I could simplify that down, but I'm not going to. And this fella here is basically just going to 1, 1. So we have y squared over 4 pi is equal to lambda, and 2xy over 4 pi also equal to lambda. And they are our system of equations now. So we started off with a puzzle. We figured out who x and y were going to be, and that gave me this constraint function. I then had to maximize the volume. So the formula of the volume looked like this. I needed to find out what all the pieces were in terms of x and y. The only one that caused trouble was the radius, so I solved here. And that became that, which became the cell. And then we did the Lagrange multiplier trick, and we're at this point here. So the first thing we're going to do is assume that lambda is 0. And if you make lambda 0, y squared over 4 pi has to be 0, which means y has to be 0. And 2xy over 4 pi essentially has to be 0, which means 2xy has to be 0, which means either x and or y equals 0. And if you put them together, the only combination that makes everybody work is 0, 0. And if you then go to this fella here, you get x plus y has to be less than or equal to 90. And technically speaking, then, isn't that a possible critical number? But is that going to be the maximum volume? No, isn't that going to be sending an empty package? Because if you make the length 0 and the girth 0, doesn't the tube disappear? So in a way, I know what the answer to that is. Isn't that the minimum size package that you can send? Which is basically you go to the post office and say, I've got this invisible tube. Can you put it in an envelope and send it for me? Would be a bit strange, but I guess you could do it. Now, if I rewrite these two equations again, and I assume that lambda is not 0. And that's so that I'm able to divide these two. Because if lambda was 0 mathematically, I wouldn't be able to, because 0 divided by 0 is a bad idea. So we have this guy being divided by this guy equals that. Now lambda divided by lambda is 1. Although that looks ugly, essentially the 4 pi's cancel each other out. And now I'm going to cancel one of the y's. Right, and we're left with that. And a little cross multiply, y will have to equal 2x. I'll then go to my constraint function, which is the x plus y, right, has to equal 90, because we've already done the inside when we made lambda 0. And so x plus 2x has to be 90. So 3x has to be 90. And so x is 30. And if x is 30 and y is twice that, it's 60. You now have the only other critical point. And if the question had been, tell me the length and tell me the girth, you would have said 30 and 60. But they put a little twist in the tail. They asked for the length and the radius. Well, I know the length is 30. If the girth is 60, and that's 2 pi times the radius, then the radius is, for that given girth, the radius is 30 over pi. And we are done. Any last minute questions? Okay, it's a very short section because we kind of started last time, so it's got 9 questions in it. I think I've done about 6 of them, so you shouldn't have too much more to catch up on. You might want to check some of the puzzle questions, especially if they change the size of something. The process won't be different, right? But the numerical answers will be. Okay, if we are good then, last name for attendance. And bye-bye for now.
Have a good day.
You too. I'll wait around in case any of you have a, I've got a